Fortune. 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 Tell Fortune to watch that cocoyam. Thank you very well. Good evening, everyone.
Good evening, ma.
Yeah.
Good evening, ma.
How has everyone been? Who have you all been? It's been quite a while. How many are we supposed to be in this class? God's rep, how many are we supposed to be in this class? Esther and Ayole Idowu. How many are we supposed to be in this class?
To be about something.
I expected everyone to be available by this time, because this class had a video, so it was not like convenient. The because I need to be here. So I was thinking that everybody wanted the class. So coming to class and missing the class MC is not encouraging.
Yeah. Some of them said they went for party and all of those. Maybe they'll join us later. Again.
Let's go ahead with the class. Now, I want to do a recap of alkanes so as to connect to alkynes. Remember, we first did alkane, which are saturated hydrocarbons. After which we did alkanes, which I can term monounsaturated hydrocarbons, because alkyne is diunsaturated. Now, what we saw in alkane is going to be similar to that of alkyne, but because alkyne has two higher degree of unsaturation, if alkane needs 2 mole to react, alkyne is going to need 4 mole. Meaning, if alkanes need 1 mole of hydrogen, alkyne will need 2 mole of hydrogen because of the higher degree of unsaturation. When we look at the slide, you realize that the slide of alkynes are shorter than that of alkanes. But remember, whatever we are teaching you in STEM is just like introduction. We don't really go into deep details. Some reactions are not being taken care of in this class. Because can the class be controlled? First of all, Esther and Ayole, can you control by the students when they come? At this level, I stated that everybody should know how to join Zoom. Whenever you're joining any Zoom, part of education is to know what to do and when to do it. As soon as you enter into any Zoom, the first thing you do is to mute yourself. That's what Courtesy demands from you. You don't enter Zoom and you're disturbing the whole class. I will start removing people. Esther, if you don't know how to do this cohort, I will put somebody else. You guys should be doing this. I think we should wait for people to come. In alkenes, in terms of reaction, if there is anything you must not forget, we talk about that whenever alkane is unsymmetrical alkane is reacting, Markovnikov's rule are being in place. In Markovnikov's rule, the carbon connected by double bond, the one that have more hydrogen is going to be giving hydrogen. The one that have less hydrogen is going to be giving halogen. That is when unsymmetrical alkanes are reacting with hydrogen halides. And we also said that this does not apply when the alkane is symmetrical. We went further to say that when you are reacting and there is hydrogen peroxide, it's indicating anti-Markovnikovs. In that sense, the carbon that have more hydrogen is going to be giving halogen. The carbon that have less hydrogen is going to be giving hydrogen. That is against Markovnikovs, which is more hydrogen have hydrogen. Finally, we talked about polymerization reaction. Where ethylene, which is a monomer, will come together via addition or condensation reaction to form a larger molecule called polymer, and the process called polymerization. And we went further to give some examples of polymers. We talk about PVC and some polymers that is available. We also talk about that polythene bag is not polythene, it's polyethylene bag. If you can forget anything, don't forget that. So whenever you want to say, give me a polythene bag, meaning it is polyethylene bag, not ethylene, it's ethylene. So in that same manner, we're going to talk about alkynes. Having knowledge of alkane will be very easy for us to deal with. So in today's class, we're going to talk about the properties of alkynes, their preparations, and their reactions. Just like alkanes are hydrocarbon, and they must have carbon-carbon triple bond. Alkanes are carbon-carbon double bond. Remember a saying that it takes two to tango. So for there to be a bond, there must be two carbon involved. Unlike in saturation of hydrocarbon, like alkane, only one carbon. That's why in alkane we start with carbon 1, methane. While in alkene and alkyne, we start with carbon 2, which is 18 or ethyne. Then, in terms of hybridization, because they have triple bond, it means that they have 2 pi bond and 1 sigma bond. While alkane, which is double bond, have 1 pi bond and 1 sigma bond. So alkyne are sp hybridized, while alkanes are sp2, alkanes are sp3. Please don't forget this. Now, in terms of bond angle, alkyne are 180 because they are linear, meaning their geometry is linear geometry. Remember that alkanes are 120 and they're trigonal planar, while alkanes are tetrahedral and are 109.5. So these are the hybridization, like we said. The properties is 180, bond angle, and linear geometry. Now, like we talked about alkane, we have terminal and internal alkynes, just like alkanes. Remember, the internal are more stable than terminal because the weights are more balanced in internal than in terminal. And in terms of molecular formula, alkyne are CnH2n minus 2, while alkane is H2n, 2n plus 2. Alkane is H2n, H2n. Please, I want you to remember the molecular formula Remember their hybridization. Remember their geometry and their bond angle. Very important. Because of the degree of, we say that the alkyne have triple bond, which introduces 2 degrees of unsaturation. Remember, alkanes, they have 1 degree. When we mean 2 degrees of unsaturation, it implies that any reaction that alkane will use 1 mole of a reactant, alkyne is going to need 2 moles of that reactant because of unsaturation. And remember, the typical reactions of unsaturation, as we are going to see in subsequent slides, are addition reaction. Unsaturation means there is emptiness, that's vacuum that to be filled. If we are available in the first class, you understand that we talked about how this hybridization are being formed. Everything occurs in p orbital. In p orbital of carbon for sp, the 2 bonds are empty. 2 orbitals were empty and they were used in forming the pi bonds. That's why we only have one p orbital participating in hybridization. So if you are not available for that class, avail yourself to go through the slide to understand how this hybridization are being formed. To give you more idea, to understand when we talk about unsaturation, you understand that the p orbital, we have 2 orbital that are vacuum in alkyne, while we have only 1 orbital that is empty in alkane. Why in alkanes, all the orbitals are filled. That's why they are saturated. And remember, when a compound is saturated, the compound are naturally inert. So they are not very reactive. So the only reaction that you can undergo when a compound is saturation is something like sim swap. We call it substitution reaction. They can also undergo something like oxidation reaction. Then in terms of alkane, they can also undergo pyrolysis. I think, but in the slide, we talked about combustion reaction because they react in oxygen in air. We termed it combustion. So that's the 3 reactions of alkanes as saturated. Why in alkanes, we are talking about because they're unsaturated, they undergo series of addition reaction. Their reaction is typical of addition to fill in the blank space. But in alkyne, because of higher degree of unsaturation, they are more hungry than alkanes. Then they will react faster and more than the alkanes, as you're going to see in the slides. Now, how do we name this compound? The same manner we named alkane and alkane. The most important thing is that the matter of so whenever you want to name, you have to give this triple bond priority by giving it the least number on the longest continuous carbon chain. So that's a priority we are considering. So if there is anything like substituent is a secondary. The primary priority is this triple bond because that's a functional group. Same thing happened in double bond alkane. When naming, you're going to give priority to this double bond. But when we are naming alkane, because alkane are saturated, so you don't think about any functional group. What to think about, looking for routes that will give the minimal sum of the substituent that is contained on longest continuous carbon chain. So these are the nomenclature of alkane. Now you can see that these are terminal alkyne. The previous slide is a normal, it can be internal, right? We look at it in internal because the terminal carbon is not where our triple bond is. So whenever the triple bond is not at the terminal carbon, we call it internal. So internal does not necessarily mean that it must divide a compound into two. No. When double bond or triple bond divides a compound into two, we say that that compound is symmetrical. Symmetrical is different from internal. Internal is when the double bond or triple bond is not on the last carbon, like we saw in the slide. Remember, it's the last carbon that bears the triple bond. So that's what we call these ones terminal alkynes. So terminal alkynes are very reactive and they are not very stable. They are more reactive than internal alkanes because they are less stable. Now, the higher the instability, the higher the reactivity. That's what happens when somebody is hungry. You know, they say a hungry man is an angry man. So that anger is instability because of what? Hunger. So that hunger makes that reaction to be high. So that's what happens for a man that is saturated, is an eternal alkyne or alkene. So their reaction is there, but they don't react like one that is terminal, that is very hungry. And remember, the fewer, the higher the reactivity. Okay, let's go. I'm still talking about naming now. Whenever you're having a compound you want to name and the compound is written with stroke or line naming. Now, if this compound is not written like the carbon and the structure that you're familiar with, we are using strokes. What you need to do is that wherever you see triple bond, that particular place of triple bond, like we can see in 4-decyne. Now, that place, we have two carbon connected by that triple bond. So this is one of the mistakes people make whenever they want to name this compound. Now, that long line is connected by 1, 2, 3, 4 carbons. Because that place that you have triple bond, I think I want to stress that place so you can see what I'm saying. I'm stressing it now. You can see there's triple bond there. That particular place of triple bond, the beginning and the ending of that triple bond are 1 carbon each, making it 2 carbon. Then the other places, we have 2 carbon. So that's why we have dec. When you count it, you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon. And in that 10 carbon, on carbon number 4, we have the triple bond. So that's why the name is called 4-decyne. We can also call it dec-4-ine. So DEC-4, then -ine. So any of them is very correct in the naming. So please, whenever you see a compound like that, don't say this is 8. It's not 8, it is 10. Now, when the next compound you're going to look at is the one that have aromatic ring. Because this compound is going to have 2 functional groups. We're having triple bond and we have double bond. How do we name this compound? Where do we start naming this compound? Now, the parent name of this compound is the one that takes priority. Just like you want to name a child, you say the child name comes first before the parent name. So the parent name is the triple bond because triple bond is elderly more than double bond. So that's why we're going to start numbering by that double bond and end up and giving this compound the parent name of triple bond. So when we start naming from double bond, you're going to have 1, 2, 3, 4, 5, 6, 7. So the compound is 7. Like I said, the place of triple bond contains the beginning and the end contains 1 carbon. So that particular triple bond, the last carbon is 2 carbons. So if you're calling it, you can call it that triple bond is terminal. The double bond is also terminal. At carbon number 5, we have aromatic ring. Wherever you see aromatic ring, as a substituent, we call them phenyl. when they are on their own, they become benzene. And when they are substituent, when they are not the parent compound, they become substituents, omoshe. When they are substituent, we call them phenyl. So at carbon number 5, we have this phenyl. Number 1 is where we have double bond. And number 6 is where we have triple bond. So I can name this compound as 5-phenyl hept 1-in-6-ine. So before that En, I can put my hept -1En-6-YNE. So it's the same thing, or I name it like it's been named on the slide, 5-phenyl 1-heptene-6-ine. So any method you use is fine. Just what the essence is for you to understand why you should put 1 before talking about 6, and why you should not start naming this compound giving triple bond carbon number 1. So we are giving double bond carbon number 1, not triple bond, because triple bond is the parent compound. Now this last compound, when you look at this compound, you realize that when you have when you are naming a compound that has both cyclic and alicyclic parts, now the one that have the highest carbon takes priority of being the parent name. So in this case, the cyclo has 6, while the alicyclic, which is straight chain, has 4. So that's why that alicyclic becomes a substituent, while the cyclo becomes the parent compound. So the parent compound here is cyclohexene. Cyclo because it's in a ring, hex because it is 6, in because it has 1 unsaturation. Now, at that compound, I have a substituent at carbon number 3. Why is it carbon number 3? Because when I'm naming this ring, I'm going to follow the route that will give this double bond the minimal number, because that is a functional group in the compound, the cyclo compound. So that's why I start from that beginning of that double bond to count 1, 2, 3. So my substituent is at carbon number 3. And what is this substituent? If you look at this substituent, it's an alkyne. And this alkyne has carbon number 4. So we call it butynyl. And that's triple bond is at carbon number 2. So that's why we say 2-butynyl cyclohexane. Just for you to understand this naming. So whenever you see a compound like that, maybe in OBG, there's something they call elimination method of answering question. You take the ones that are not it, then you will left with the ones that are likely. So then from there you can do your final elimination. So when I see this a compound like this, what I need to do, I will look for the one that does not talk about cyclohexane. I eliminate them. Then I will talk about the position of the substituent. The one that did not tell me that the substituent is carbon number 3, I will eliminate. Then I'll finally talk about the name of the substituent itself. That's how I finally get my answer. I hope that makes sense. From the previous class, we've talked about what isomerism is. And we said that isomerism is like twins. These are compounds. What don't you understand, Ayole? You can unmute and talk. The class is waiting for your question. Can you unmute and talk?
Yes, ma'am. Because we are talking about alkyne, and this first one, there is no triple bond, there is just double bond. Why do you see butyl?
Sorry, everything we have here is triple bond. Is a diagram. Which of them are you talking about?
the last one you did, that 3-butyl cyclohexane. Because the last one you did, you can see that they are aromatic. You can see that the first one is 1, 2, 3, but this one is 1, 2. I can see just two stroke of line there.
The last one we did, this cyclo compound, the alkyne there has triple bond.
Okay.
Do you understand that? So
Just,
that's what I want to
yes,
stress
this.
everything now. So I'm stressing everything so you can see it. So when you get your slide, you see it. All of them are triple bonds. Is it visible now?
Okay.
Are you
But
okay now,
okay.
Yoli?
It's because they are not triple on the aromatic, but in the previous they are triple on the lines of where the carbon is. So that's why I'm confused
Now,
that why are they not
okay.
triple on that
So it doesn't
lines?
matter now. Remember, like no, okay, like I said, whenever you have a compound that has two sides, alicyclic and cyclic, ring and straight chain, the one that has the highest number of carbon takes priority. Now, if that last compound we named, we are naming it as a hexane, not hexane, because the ring is cyclohexane and it has higher number of carbon than the alkyne. So the alkyne becomes a substituent. Do you understand that?
Okay.
Alkyne has 4 number of carbon. That's a straight chain. While the ring has 6, which is double bond. Triple bond has 4. So in that case, the person will get money, now they will. So that is why hexane is ruling here. Despite that alkyne is there. Alkyne is so if nomenclature too. So the one that have the highest number of carbon there's going to be given priority as a parent name, or that becomes substituent. Do you understand that? So that's why we have 3, because at carbon number 3, that's why we have that substituent. And the substituent we have is 2-butanyl. So that is a substituent. And the compound, the parent compound is cyclohexane. So that's why we have 3-2-butanyl, then closed cyclohexane. Who else have question? Let me hear your question. Peter and Balogu Lukman, one after the other.
Yes, ma, please. Yes, ma. So very quick, sorry for dragging us back. So for the third one, ma, the 5-phenyl 1-18-6 and 6.
Yes.
Because I want to know how we got the total longest carbon as 7. Just that, ma. How we got that 7?
Now.
I missed that, sorry.
Okay. Now, between triple bond, how many, the terminal carbon of triple bond, how many carbon do we have there?
2 carbon. 2 carbon.
2 carbon. The third carbon that has the phenyl making it how many carbon?
Sorry, I didn't get the question.
Just name it, number it first. The first carbon, remember we're starting from carbon that bears double bond, right?
Yeah, but the one with triple bond should we not consider it first? Since it has more carbon power.
Remember I said it. The straight chain is the longest carbon. So the straight chain is 7. So phenyl is a substituent. In naming this straight chain, because we have 2 functional groups.
Okay.
the higher functional group is going to be the parent name. The lower functional group is going to be a substituent. So it is like the lower ones is going to be named first. Just like your name is Alex Okoro. That Alex is your name. That Okoro is your parent name. So in that case, the triple bond is like the parent because it's higher. So double bond will come first before it comes. Yeah. So that's why we are starting by numbering from the double bond functional group. But in the four decyl, we have only one functional group. Please take priority. So we are giving it priority by giving it the minimal number. But when we have more than one functional group, that the highest one becomes the parent compound. Others becomes a homo that will come. So we name the compound by virtue of the highest functional group. Just like when you have a compound that bears hydroxy group and carboxylic acid. That hydroxy group becomes a substituent. Carboxylic group becomes a parent compound. We call it hydroxy acid. Do you understand what I'm saying?
Yes, I'm assuming.
That's the sense of functional group priority. We have the bigger one swallows the smaller ones. So wherever the bigger ones are, smaller ones will not talk. Wherever they are told to stay, they will stay. Just like as we are now. If you're married and you have a child, where you are, your child cannot talk because you are there. It's when you're not there, your child represents you. So that's what happens in nomenclature. Now, because we have double bond and triple bond is the baba. So double bond is going to go first, where triple bond follows and cover everybody. So now when we are naming, when we start counting, the terminal carbon of that double bond have 2 carbons. Triple bond have 2 carbons. So making it 4. So the other ones is 5, 6, 7. So that we have 7.
Okay, so if we are to draw this in a straight chain, that means from the part of the triple bond, there is C attached to triple bond, another C. So it's not just it's not just the C attached to the aromatic, then to that of the triple bond.
I keep saying it that whenever you have bonds, when I was starting this class, I said
it's carbon to carbon between them.
Yes.
Yeah. Exactly.
So whenever there is double bond or triple bond, there must be 2 carbon that form that bond.
Very
so
clear.
That's just
very clear. Thank you very much, Ms. Claire. Thank you.
All right.
Sorry, ma.
Okay.
Good afternoon, ma. Yeah. Please, ma, I would like you to throw more light on this 3,2-butynyl cyclohexene, ma. The naming, because I'm trying to look at the place where we started the naming from, so that I can get it clear, ma. Thank you, ma.
Where you're starting the naming from is functional group. Where is the functional group?
The functional group here is where the one that is the attachment, that is 1, 2, 3, 4. That's the butynyl.
That's not okay. Which other functional group do we have?
You said, ma, that the naming, we are going to consider the one that has the highest number of carbon. So, and I believe the cyclohexene has highest number of carbon than the attachment, which is the butynyl.
Okay. So the cyclohexane, where is it? Does it have a functional group?
Yes, which is the double bond.
Okay. So if I want to name, forget about the attachment. If I want to name this cyclohexane, where will I start? If I want to number it, where will I start numbering?
Then we start from where the double bond is.
Okay, so start from that and number. Let's see.
So that will be 1, 2, 3. Okay, I get now. So that carbon 3. So that carbon 3 will be 3-cyclohexene. Okay, why the butynyl will be named separately? Okay, thank you, ma. I've gotten it.
Okay, fine. Thank you. So who else? Balogu.
I've just been attended to, ma.
Okay. So I think can we continue now?
Yes, ma, we can. We can. Thank you, ma.
We can be on the same page. Okay, like I said in isomerism. Isomers, you must understand what is isomerism. You must understand types of isomerism. You should be able to give us examples of isomerism. Whenever you're told to answer question on isomerism, you are expected. You cannot be given example of twins and you're going to use one structure to represent twins. That's a mistake some students make. If they want to talk about chain isomerism, they will give us one structure. It does not make isomer. Isomer is twins. So if you want to tell us these are twins, you have to tell us A and B and why they are twins and where they are differentiated. So whenever you're answering question on isomerism, I say examples, give us two structures that said this is this and this is it. Remember, isomers are compounds that have the same atomic molecular formula, but they differ in their arrangement in space. Their difference is they have the same number of carbon and hydrogen. They have the same number of carbon, hydrogen, oxygen, or whatever. But their difference is the way they are being arranged. Some are terminal, some are internal. So that's why make them isomers. So isomers are twins that have the same age, but they differ with one thing or the other. So isomerism is a phenomenon whereby a compound have the same molecular formula, but different structural formula. Why? Because of different in arrangement in space. So now, in terms of alkane, we have isomers. We have isomers in alkyne. Now, isomerism in alkyne starts from third member, which is butane. Now, the first and second members at a time do not show isomerism. Why? Remember, if you look at ethyne, is the first member of alkane and alkyne. Where will you rearrange them? They are just the straight line. They cannot be rearranged. If you look at prop, wherever you put the triple bond, either it is terminal by the left or it's terminal by the right. So there's no change. So that's why both ethyne and propyne and ethene and ethyne cannot, because wherever you put them, they're still representing either terminal, they're still representing terminal alkane or alkyne. But in terms of boots, I can have boot 1, I can also have boot 2. So I cannot have prop 2, I can only have prop 1. So that's why prop and et cannot, but boot can. In terms of isomerism, alkyne exhibit chain, position, and functional isomerism. Let's look at example of the isomerism. Do you understand what I explained in isomerism? Now, the isomerism you're going to get in unsaturation is mainly chain isomerism. Is mainly chain and position isomerism. In the sense that, remember, we are dealing with double bond or triple bond. When I shift, when I have terminal and internal, the difference between them is their position. They are the same number of carbon and hydrogen, but the position of this double bond make them positional isomers. Now, another one is that when I have a longer one, from that position, I can form another one called chain, where I have a straight chain and a branch chain. Now, let's look at the example of chain isomerism. If we look at the first one, we are looking at pent. This pent, I can have position isomerism from pent, and I can have chain. From my position isomerism, we can have pent 1 ine. We can also have pent 2 ine. But from my chain isomerism, you can see we can have from straight chain and we have from branch chain. We have 3-methyl but 1 ine as our branch chain. So from pent1-ine and pent2-ine. These are number one example of isomerism called position isomerism. But from pent1-ine and 2-methyl-but1-ine, I'm forming another isomer, which is chain isomerism. From straight chain to branch chain is chain. But from position 1 to position 2 is position isomerism. So this is position isomerism now. I have but1-ine, I have but2-ine. I have pent1-ine, I have pent2-ine. These are called position isomerism. So these are the most important isomerism that is very applicable in unsaturation of alkane and alkyne. But if you come to alkane, alkane can have chain isomerism, position isomerism, functional group isomerism. But the one that is most important in unsaturation is chain and position. The physical properties of alkyne is similar to that of alkanes of comparable molecular weight. An alkane too of comparable molecular weight. Difference is that they have lower melting point and boiling point. And their melting point and boiling point increases as the number of carbon atoms increases, just like other hydrocarbons. They are soluble in organic solvents like alcohol, and are insoluble in water because they are non-polar. These are their physical properties. So which are also being explained further here. You can see the more the carbon increases, look at what happened to their melting points. So the same thing that we explained in alkane is applicable here. Remember I said alkane and alkyne, they have so many things in similar. They have so much similarity. The only difference is their degree of unsaturation, which also affects their reactivity, making alkyne more reactive than alkanes. So how do we prepare these alkynes? The most common method of preparation of alkyne is from acetylene. Remember, acetylene is the commonest alkyne. We are preparing them from carbide, calcium carbide. From calcium carbide, under hydrolysis, we're going to form calcium hydroxide and acetylene. Under pyrolysis, at very high temperature, we can also form this acetylene. What is more important in this alkane and alkyne is their reaction. And all their reaction is reduction. Now, they undergo addition reaction. Whenever you're adding hydrogen, remember I said hydrogenation is a reductive reaction. They undergo hydrogenation, which is addition of hydrogen. They undergo halogenation, which is addition of halogen. They also undergo hydrohalogenation, which is addition of hydrogen halide. These are the common reactions these undergo. The same way they do in alkane, the same way it happens here. Now, if I remember alkyne, let's look at some of the first reactions of alkyne don't need Markovnikov. Look at this. Look at the I'm trying to stress this for you to understand. I'm not going to read the slide for you. I want to explain the equation. So when you read the slide, you understand what I'm explaining better. Now look at this bond. Because we only have 2 carbons, meaning that this compound can be assumed to be symmetrical. So if I want to react with any hydrogen halide, I'm not going to think about Markovnikov's rule because it's symmetrical. Immediately I form the first reaction, my compound become asymmetrical. they become asymmetrical. In that case, I can go ahead and apply Markovnikov's rule. But in the first one, they are symmetrical, so I can do anything. So remember, you can only apply Markovnikov's rule when there is asymmetrical reactions. But if not, if I want to add hydrogen, if I want to hydrogenate both in alkane and alkyne, I don't think about Markovnikov's rule. Markovnikov's rule only come to play when I'm dealing with hydrogen halide across double bond, not triple bond, because triple bond, the same number of carbon and hydrogen are always similar. So we only start that when we are dealing with asymmetrical compounds. Hydrogenation of alkanes is the same.
Please, so can you hear anything?
I know they hear anything.
No.
You
I
muted
can't
us.
hear. I think the network logged out.
I was logged out. Sorry, I was logged out. Okay, so like I said, whenever we are hydrogenating alkyne, the intermediate is going to be alkane before forming alkane. So in hydrogenation, alkyne will move from alkane to alkane, from alkane to alkane. But if I want to make it to be one-time reaction, I will just use 2 mole of hydrogen to form my alkane. But if I want to make it normal step reaction, I'll first of all hydrogenate to form alkane, then hydrogenate alkane to form alkane. Remember, whenever you're doing hydrogenation, don't forget your catalyst, which can either be platinum, palladium, nickel, or rhodium. This is a reaction. Now, A does not follow. Then when you talk about B, we talk about Markovnikov's orientation. Why? Because at that moment, the compound is now asymmetrical. But just let's look at this last slide. If you look at the first reaction, the first one we're going to have symmetrical. The first starting material is symmetrical. So when we react, anything can happen anyhow. Then when we enter the second one, you realize that it's not more symmetrical. It has become asymmetrical. So we can apply Markovnikov's. But look at the last compound, which is what? Prop 1 ion. Is that compound symmetrical or asymmetrical? Somebody should answer my question. Esther.
It's asymmetrical, man.
Who can answer? Who is answering?
I can look, man. I think it's asymmetrical, man.
Is asymmetrical, very well. So because of that, I have to apply what? Markovnikov's orientation. So whenever I see a compound that is asymmetrical and I want to react hydrogen halide, please, if it's not indicated for it to be, if there is no peroxide, employ Markovnikovs in writing the products of that reaction. Except otherwise, there is hydrogen peroxide as part of the reagent. It means that it's anti-Markovnikovs. But when you are having a compound that is symmetrical and there is hydrogen halide as a reactant, because it's symmetrical, you don't need to think about Markovnikovs. This will help you in every reaction that has to do with unsaturation and hydrogen halide. It's a rule that does not stop here as long as chemistry is concerned. So let it be part of you in terms as a chemist. So that's why the second prop 1 ion, I'm going to apply Markovnikovs because it's asymmetrical to form my product. So when I apply in the same, the intermediate is still asymmetrical. So I'll say apply Markovnikovs to form my product. So in the exam hall, if you're giving a compound like this, you might be giving a product that is maybe the first one might be correct, and the second one they will come and give you anti-Markovnikovs, where hydrogen will come to replace chlorine and the chlorine will replace hydrogen. So if you don't understand, you become confused. Just understand what you're doing. Don't look at the answer without understanding what you're expecting. So that, because at times some of these things, different might be small things. So if you don't have an ego eye, you can only understand that when you've submitted your paper. So that's why you have to look with ego eyes. Whenever you're entering the exam hall, if it's OBJ, make sure you have double goggle. So this is following Markovnikov's rule because what it is asymmetrical. Alkyne are slightly less reactive than alkanes. Why? But we expected it to be more reactive. Why is it less reactive? Someone should answer me. Can somebody answer this question? Should I make it to part of homework? Why is it looking like they are? Why are they less reactive? From the equation we are having, you can think out of the box. But they are supposed to be more reactive because they have more space. But why are they less reactive? Can anybody try? Yes, try.
Maybe we'll say
Who is talking? Let's talk because I want us to do aromatic compounds. Can we talk? Nobody is beating you. Just try.
Okay, ma. According to looking at the reaction between this compound and HBr, the halogen is attached to the side that has more hydrogen, while the hydrogen is attached to the side that has less hydrogen. So the HBr, the reaction for the HBr, the halogens, I'm just trying, ma. I think it's going to be at the reverse manner. That is, HCl is less than HBr, HBr is less than HF, or something like that. I don't know.
Okay. You're talking about in terms of the halogen. Okay.
Yes, ma. I want to try, ma.
Okay.
So because alkynes, if you look at their bonds, alkynes have you mentioned they have 2 pi bonds and 1 sigma. Alkene has just 1 sigma, I think, and 1 pi. So alkyne, they have more density, right? They have higher density. That would make them lesser reactive to alkenes, because alkenes will still be looking for more electrophiles to join them. But alkynes will already have like more electrophiles that are willing to, attach to their own bond due to higher density in their carbon-to-carbon bond.
Are you trying to tell us that alkenes are more reactive or what you said?
Yes, alkenes are more reactive because they have less density in their carbon-to-carbon bond than alkyne.
Okay. Who else want to talk?
I want to try, man.
Okay.
I think the reason why the alkynes are slightly less reactive compared to alkene is because they are not as saturated as alkyne. Alkyne are not as saturated as alkene.
Okay. There's something I'm looking for.
Yes, ma'am.
Now, you guys have a point. Mohammed, alkene.
Yes, ma'am. Yes, ma'am. It's
Yes, ma'am. Okay.
we're talking about alkenes. Basically, when we talk about their electronic structures and their bonding characteristics, the carbon atoms are sp hybridization.
Okay.
Yes, ma'am.
Okay. Thank you very much. See,
Yes, ma'am.
the simple truths that make this one slightly
Can I
less
come?
reactive.
Okay.
Talk. I like it.
Yes, my submission has to be with the bond angle for alkyne is 180 because of the straight chain. Yes, as compared to that of alkenes.
Okay, good. Now, why I'm happy with all these questions is that it seems that you guys are understanding the nitty-gritty of this chemistry of alkene and alkyne. But the quickest way of solving this problem is, now remember, in alkene, I just have to break one bond. Why in alkyne, I need to break two bonds. But though those bonds are weaker bonds, but I still need to break them. So I need more energy to break two bonds than I will need to break one bond, right? So that is the reason why alkenes are more reactive, because they just have one step to form a saturated compound. Just like people are going, like I have two carryovers and somebody have one carryover. The person that has more work to do is me that have two carryovers. Even if the carryover I have is small is 1 unit course, they are carryovers. The energy is going to take me to reach two courses. It will not be the same as the energy if you take the other person that had one carryover to read one course. So because of this double bond, though they are weak. Now, if you talk about being hungry, be empty, alkyne are more empty. Now, it means that if it is more empty, now the much food that you can feed alkyne to make alkyne to be okay is more than the one you're going to give alkene that has just one space. So that's a slight change in their reactivity. They are both hungry, highly unstable. But before you saturate alkyne, you've saturated alkenes too of it. So in terms of that, that's why they call it slightly very less reactive, because both of them are on saturation. But in terms of highly unsaturation, I need more to feel alkyne that I will need to feel alkene. I need to work harder to feel alkyne. So that's the difference between their reactivity. Like I said, it's only when there's problem of hydrogen peroxide. That's why we'll talk about anti-Markovnikovs. So that's the same thing we are seeing here. Anti-Markovnikovs, the presence of hydrogen peroxide. meaning the carbon that have more hydrogen, you can see now is giving halogen. The carbon that does not have less, that have less hydrogen is giving hydrogen. So now remember, like I said, that this peroxide, I can use my formula to write the peroxide. That's H2O2. So either I see peroxide or I see H2O2. I'm still saying the same thing. Talking about anti-Markovnikov. That's opposite of Markovnikov's rule. So you just have to get used to Markovnikov's or anti-Markovnikov's. Remember, this happens only to hydrogen halide. So when I'm doing with halogen, I don't need Markovnikov's. I can add them however I want them because I'm adding the same thing. So halogenation and hydrogenation does not involve Markovnikov's. So ask your questions because I want us to enter into another slide, which might be the last slide, so that any far we can go on that slide. The next we'll finish it and then do general revision. When is your exams coming?
On the 23rd,
Eh?
on the 23rd of next month.
Of September.
Yes, ma'am.
Yes, ma'am.
I even have plenty time, sir. We are going to have a general test, which is your CA. So after
Online?
Yes, they're going to do it online. We're going to do it online. And that online, we have to have a starting time and ending time. Everybody will do it at the same time. So the next topic I want us to talk about now is aromatic compound, benzene and aromaticity. So when we are done with that, I will do general revision. So after giving you that benzene, that's when I want to give you general revision question. But I will also give you questions for nomenclature, different. So I want you to have your hands on how to name alkanes, alkynes, along with alkanes. Because the general revision will be the final revision I'm going to give you before we do the test online. Any question on this alkyne so that we can go to the next slide?
Sorry, ma. Please, ma. Regarding the last slide, ma, where you were talking about the slight difference in the reactivity between alkynes and alkenes. So the explanation, what I can decode from it, is that the explanation for the slight reactivity is based on the energy required to breaking
Break the bond, yes.
the bond,
Yes,
the
yes,
2-pi bond that is
yes,
in the alkyne. Okay.
yes.
So what I'm trying to say is that can that be related with the bond energies?
Yeah, that's why I say bond energy, yes, because bond energy is energy to break the bond. That's the bond energy.
Okay, I get you, ma. Thank you, ma.
So can we go to the next slide? I want to assume that nobody have question on alkyne. Because if you were in the class for alkene, you will not have issue with alkyne. Some people were not in class with them.
Yes, ma'am. I think we really did not dwell with the preparation of our kind. We just scroll the slide.
Okay. Ayole, are you the one that just talked?
Yes, I'm gonna ask a question now.
Okay, I'll send the slide. So
No, I'm not saying
select.
I'm not talking about the slide, man. I said
You're talking about what?
do not dwell on the preparation of our kinds. We just scroll the slide. We not really talk about it. I don't know if it's
There's nothing much in that preparation of alkyne. If alkyne, like I said, I'll say
to me, it's much.
what is important is something you can read and understand. There's no much deal about it. It's just one reaction. first one is produced from calcium carbide, reaction of calcium carbide and water. That's the first method of preparation of alkyne. Then the other method, as I said, is from pyrolysis. When methane is being heated at very high temperature, they form alkyne. So, as I said, it's not a serious matter. So the calcium carbide in water, then industrially from pyrolysis. That's what you need to know about. There's no big deal about alkyne and reaction.
Okay, ma. Sorry, ma. Again, ma. I want to ask another question regarding our knowledge as regards the reaction of our alkynes.
Yeah.
Taking it from alkenes, alkenes undergo combustion, addition, polymerization, and oxidation reaction. So I just want to know
Alkanes. Are you talking about
alkene,
alkane?
alkene, yes, ENE,
Okay.
yes. So what I'm
Now
trying to
listen.
ask,
Remember,
yes,
if you look at alkyne and alkane, okay, ask your question.
continue, ma. I just want to continue.
No.
Yes.
Continue.
Okay.
Let me understand your question very well.
Okay, what I'm trying to say is that so that we know our area of focus for the purpose of our exams when we are reading. So in order to know the area, so we are going to dwell really on these alkenes and alkynes. So I don't know whether we should explore more on the reactions and the reagents that will lead to the product and the product that will be formed on the areas that we are going to leverage on.
Now, when you want to read all these reactions, just like alkane and alkyne, something is common among them: addition reactions. If you look at alkane, has more reaction than alkyne, right? Because beyond addition reaction, alkene undergo oxidation reaction, right? They also undergo polymerization reaction. Alkyne cannot undergo polymerization
Okay, ma'am.
because the polymer is acetylene, is alkene, right? Now, ethylene is the polymer. So, because of that, remember we said that alkene are slightly reactive than alkynes. Alkanes are more reactive than alkynes slightly. You can now, like this issue of hydration, it can undergo hydration, it can undergo oxidation and others, which alkyne cannot undergo. Now, whenever you're looking at, if the question is talking about reactions of alkanes, you're going beyond addition reaction. You can do addition reaction, you can talk about oxidation reaction. Now, but if the question is that example of addition reactions of alkanes, then you can leverage on hydrogenation, halogenation, and hydrohalogenation. You can leverage on the three addition reactions.
Okay, ma'am.
But if
Okay.
now it depends on the question. But if whenever you're dealing with reaction, like in your theory, I'm not talking about OBJ because OBJ will tell you whether they are talking about reagent or they're talking about product. But in your theory, if you ask reactions of alkene, with detailed equation, show 3 named reactions of alkene. Now, you're not talking about the addition reactions of alkene. You select if it's any of the 3, whether you want to leverage on addition reaction or you want to talk of both addition and combustion reaction, but you have to name it. If you want to leverage on the addition reaction, you tell us you're doing halogenation reaction. In that halogenation reaction, you give us a named one. If you want to talk about propane reacting with hydrogen to form propane, tell us that is propane. And tell us the hydrogen. And tell us that I need a catalyst to do it. So let that be detailed reaction, including their requirements. Now, for each of the named reaction, don't talk about hydrogenation and you're doing halogenation. So now, the simplicity of it is that make sure you understand anyone you want to understand. Don't read. That's why I normally advise students. And when don't read because tomorrow is exam. After each class, make sure you go through whatever you're taught that day, because it's going to help you to get acquainted with what you've learned. It will make those things to enter more. So that when you're conversant with your slide or with your notes, exam is just like revision. You cannot stay awake all night because you have an exam tomorrow. Because when you enter exam hall, you'll be confused because your system will not be in equilibrium to reason. But when you're reading every time, you're always going through your slide, what does not make sense will consciously become part of you. Now, when you're in the exam hall, you don't need to struggle. Just like some songs you sing without even reading the lyrics. So, chemistry is like mathematics. Make it your friend. Make sure you visit chemistry every day. Even if it's 5 minutes, maybe that's why some of these things are online. You're traveling or you're not driving, you're going to work. You can just connect and listen to the class again. The more you listen to them, the more they become part of you. So whenever you want to sit down to study to read, it's like you've read them before. You're just revising. So in the exam hall, you don't mobile hydrogenation with halogenation. So like I said, I will not say, if I come and give you all the questions I want to set, no need of setting the questions, no need of grading you. But because I understand some of us are not does not have this basic chemistry class, that's why in my question I make sure I go as elementary as possible, because the essence of this is for you to have the basic knowledge of organic chemistry. Some of the things I'm telling you here, just like talking about, I cannot tell you to give me the reaction, how to prepare alkyne or how to prepare alkene. But just for you to understand it so that tomorrow, when someone is talking about calcium carbide, you realize water forming alkyne. You realize that, I think I've had something like this before. It will not be like a news. So that's the essence of this knowledge. So don't ever read because you want to pass exam. Just read because you want to understand the concept. Then exam is a secondary matter. Your exams are not going to be difficult. I don't know whether you guys have access to past questions.
We don't have,
Do
ma.
you have access to? Okay. So if you don't have access to past questions, you will not have issue, because anything I'm giving you something you can easily, as long as you're in the class and as long as you're participating in my classwork on the assignments, you're good to go. Just don't, whenever I give you assignment, don't go and copy from somebody. Understand the assignment you're doing. And if it's not clear and what you wrote, you're not sure, because the truth is that because of the number you guys are and it's online, it's always not easy for me to assess everything. But when I finish my class, I will make sure I go through some of those assignments so that you guys understand what you did right and what you did wrong to prepare you for the exams. So in conclusion, when you ask equation in theory, you're expected to tell us the reactant, the reagent, and the products. And the products we are expecting is the major products, not the side products. Any question on that?
Yes, ma. Good evening, ma.
Yeah.
Yes, ma. Ma, you said alkyne does not undergo polymerization reaction. But there was this textbook I read about biochemistry, and I saw that you can have like 3 times together to give you benzene. So I don't know. Is that not polymerization reaction?
No. Polymerization is polymer. Do you know what is polymer? If you go to the last slide, we talk about alkene. You see how polymerization occurs. Polymerization will form a very large molecule, not three, not benzene. Benzene is not a polymer.
Okay, ma'am.
But benzene is not a polymer. Polymer is polyethylene. Polymer is giant molecule. Is hexene giant? Is 6 giant? 6 is not giant. So for ethylene, for alkyne to undergo polymerization, we would have undergo addition reaction to form ethene or alkene. Can I hear you? Next question. As long as regarding this class, this basic organic chemistry, please, the slide is enough for you to pass your exam very well. Don't give yourself unnecessary tension, except you want to go further in organic chemistry. When the class started, I wanted to go further to talk about alcohol and acid and everything. So they said no, they don't want the student to be scared. They just want it to be basic. So that's why I ended in hydrocarbons, then added the aromatic compound, which we're supposed to do today. Maybe we'll do it in the next class. So I wanted to talk about, I'm going to share the slide. So in the next slide class, you can use 1 hour to finish that benzene and aromaticity. So when I share the slide, you have to make sure you go through the slides. So just have a full sight, or just, even if it doesn't make sense, just look at it. And remember, all these topics treated on my YouTube channel. So if you want to you like chemistry, you want to go deeper in alkyne, in all that we have treated, and want to know much more about organic chemistry, the basic organic chemistry class is online. So you can read further to know more about chemistry, especially for people that are in chemistry major. Amen. So any questions so far on this? So we can round up for today. I scheduled for 1 hour 30 minutes because it's weekend. We cannot overstretch it that we have so much to do. So you can have time to attend to your families too. So any other question? Any question? So if you have question, unmute and ask. And if you don't have question, thank you very much everyone for coming. So we'll see in the next class. When is the next class? Ayole and Esther. Let's know the next time we can round up this section.
I will communicate with you, ma.
And please, whenever you're reading, I want to encourage us to read all that we've done so far. So in the next class, if we're able to finish on time, I can attend to all your questions. So you cannot have questions except to read. So make sure you read something.
Thank you.
Even if your questions are feeling funny, because that's why you came. You came to learn. Don't feel they will say I don't know. It doesn't matter. So ask any question that you don't understand, so we can treat it together. Because the essence is I want everybody to have A, a minimum of B in this organic section, and I know it's very possible. So I wish you the best. I will try and send the hands-on nomenclature on hydrocarbons, alkane, and alkyne. So Esther and Ayole, remind me. Yeah. Okay. Thank you very much. Enjoy your evening.
Thank you. I will explain what the slide is about. I will explain the slide.
Yeah, just okay, sure. I will just share the slide now. Thank you.
I have not sent the link for the health stuff.
Sorry, Shebi, I've sent the alkane slide.
No, the link that you said about that block group should not eat and the like.
Okay. Okay. Let me send it on this slide, on this place. Let me send it on the chat here. Let's send it on the chat. When you go to Google, just click at Dr. Anita. When you click Ask Dr. Anita, that is my YouTube channel for health. Why Dr. Anita came is for chemistry. All right, everyone. It's nice having us because it's been a lot. I was like, hey, I'm sorry for not being available all this while. But no worry, we are finishing in the next class. I'm always the first to finish, so that's why I don't bother. Yes, you're going to just do what I said. The organic chemistry is simple. All right. Enjoy your weekends. Bye for now.
Okay, let's continue the class, everybody.
Go ahead.
Three boots, 1 9. 3 boots, 1 9. Ester Ifemode nitrobenzene.
What's that?
And
Oh,
Who is that
wait,
one?
I will keep it so. No.
Mr. Yole, are you there? Mr. Yole, are you there?
Chemistry is not chemistry at all.
I beg all this alake, please help. Somebody should help.
Today's chemistry is not chemistry. Come on, Kuro. Hold on.
In fact,
It is alake.
in fact,
Just saying alake.
I'm feeling very happy here right now.
Alpha.
I am feeling very blessed right here. That's why I'm directing that question. May the woman give us past question. No waiting.
Alpha.
That question is the best.
Honestly, I didn't understand you. I know where they go, but the woman turn you. You just look for way to turn the question.
I just lock up sharp. Because all this one where we just dey see every molecule dey fly for air, dey fly for heaven. So hear me o. Now this kind thing we wan still hard more to. You wan hard more to this kind thing.
One of my colleagues
Today's chemistry at all.
So funny. Oh, dear, actually.
Please,
Hello, Mr. Lukman.
Yes,
Mr.
ma'am.
Lukman.
Yes, ma'am.
This thing Mr. or Professor Sonny talked about. That link he said he's going to share for questionnaire. Has he shared it?
No, I never see any link. After our guy.
No, he said class rep should remind him.
Now better Marco. I don't even set whatever. Like everything else, I put all say that.
See, I beg
so that he will remind him before that man will come and say something else again.
Please, so everybody, I beg, if you get a better note on Dr. Mrs. Shobowale's entrepreneurship, I beg, we can send though. I beg you now.
How many times will I send that note? How many times? I don't send that note more than 10 times on that your platform.
Towards this last part now, not the first part. All the remaining.
Please, resend the note, please.
I beg.
Okay.
I beg. If I see you, I will take you to Mr. Big to go and see what they are selling.
That's why they said buy something for me. Just imagine. Don't kill me. Oh.
I don't get any class every start of day. I don't dey talk am down now like this. I get fight, you fight to, you go fight to. I don't dey talk am down like this. I know we dey chop chicken, on the face pass. I don't dey talk am down like this. I beg go.